So, welcome to this third lecture on the fourth week. You would see today we are also going to talk about the relationship between mathematics and physics. Essentially, mathematics here, our story would be relating to the use of vector valued functions in classical mechanics. Classical mechanics or Newtonian mechanics is still one of the most fundamental and most important areas of science. It describes the world around us as we see it, and most of the things that we do in daily life falls under its purview. So, it's good to have some idea of it and how to handle it mathematically, because mathematics seem to be one of the most important tools by which the laws of nature can be described without any ambiguity. And there has been a very famous article by a physicist called Eugen Wigner, which says the title was "The Unreasonable Effectiveness of Mathematics in Physics." So, mathematics and physics, there is, even in the modern setting, there is always a back and forth game that goes on, that one really is linked with the others. So, for example, we had already studied that suppose a particle starts at time t0 and till t1 it moves along a certain trajectory. So, this is where it starts, this is a start point, and this is the end point. Okay. And now at every point this is my vector, the radius vector, which we have already said, described earlier, is r_t0. So, this is at any arbit time t in between t and t naught, this is the position of the particle, which is written as r of t. And at the end point, of course, you will have RT1. So, RT in some sense describes the path of the particle, and that is what we have discussed earlier when we tried to link it up with physics. This whole idea can be taken to infinite dimensions also. RT could be higher dimensions also, means not infinite dimensions, it could be in 4 dimensions, 5 dimensions, 6 dimensions, does not matter. So, RT in general is expressed by the 3 coordinates which keeps on changing with time. So, xt is a function of time, yt is a function of time, and zt, the x, y and z coordinates are the functions of time. So, r itself, the radius vector function, can be viewed interval t0 to t1. To the real number line. No, sorry, not to the real number line, to the real 3D space R3. So, here is an example of vector valued function, right, from 1 dimensional space to 3 dimensional space. And we all know how these kinds of functions, so any such function RT, this R function is usually called, we call it the radius vector as physicists would like to call it, but sometimes in mathematics, at least in this book, R is called the path function, because it describes the path of the particle by describing its position at every time instant t. Okay. R is called the path function. This path function need not be only thought out in 3 dimension, as I said. You could think about a path function say from A to B in R to Rn, that is, take any t lying between A to B, and this Ct can be viewed as consisting of n coordinates which changes with time. Of course, it does not have physical meaning when you write a thing like this. It does not have, it cannot you talk it with the in terms of the particle, but you can definitely say that fine, I can attach meaning, whatever I know for the particle can be brought in out here. For example, now let me talk about how to talk about the velocity of the particle. Velocity of the particle, you know, for a particle it is given as r dot t, which is d of rt dt, and this is nothing but taking the derivative of the scalar functions with respect to t. So, for a path function in Rn, c dash t instead of dot is essentially for the change with respect to time. Here the t variable could be any variable. For this t, it could be any variable, it does not always need to represent time, but for physics, for the radius vector, for a particle motion, it needs to talk about time. T is been said to be time. For particle motion, just let me write, for particle motion, t refers to time. So, when you know that you have acquired some idea of how to define, so for example, if you take the vector Ct and take the derivative c dot t, what we have done for this Rn function, AB to Rn function, then this is nothing but x1 dash t. We will not write c dot t, but we will write rather c dash t, telling that it is derivative with respect to some variable t which need not be time. We put the dot when we want to mention, when we want to be sure that the time, the t variable is actually time. When I am having time, I call it x dot t. That is the symbol of Leibniz, who give this kind of, you use this kind of symbols. These ddt of rt, these sort of things became much more popular with Euler later on. So that is how the derivative for Ct is calculated, right? So you know this. This is how the derivative of Ct is calculated. So now once you have this, we can talk about differentiation rules for differentiation, because now we will have vectors. So we will have multiplication, mean we will have dot products and we will have cross products. So how are we going to write those kinds of rules? So let us write down the rules for differentiation. So if you write down the rules, we will go one by one. The sum rule, then you will have ddt of any vector valued function, say bt and ct as per the book, or whatever you want to say, at plus bt. So you take the sum of these two functions, and this is, you can immediately understand, I do not have to write down this rule to you, that the sum of the derivatives. So sum rule is known to you. So, there is something called scalar multiplication rule. So, what is the scalar multiplication rule? In the scalar multiplication rule, you bring in a scalar function Pt. So, t is from say ab, that interval to r. So, p is a real valued function or scalar function. We are only concerned with real valued function. There could be complex valued function, all those sorts of stories you will hear, but you just bother about this, nothing more. Okay. So, in that case, what is the rule? Then ddt of pt scalar into some bt, which is the scalar function, right? I should put the, in a scalar function I should always put the arrow, that is what I am forgetting here. Sorry, in the vector function I should always put the arrow, for the scalar function I am not putting the arrow. Is, now it is a product rule. How are you going to do this? So, it is like this, it is a standard thing, P dash t into Bt plus Pt into B dash t. So, you see you have to write it in the form of a product rule. So, the rules do not end here, the rules continue. Now comes a much more interesting rule, which is called the dot product rule. So, what does this dot product rule does? This dot product rule does the following. So, you have two vector functions bt and ct, and you want to know that if you take the dot products, which is a scalar, then what would happen? How do you write the product rule? The product rule again relies on the dot product. So, it's b dash t, I am writing b dash because t may not be just time, t could be any parameter, dot ct plus bt dot c dash t. Note that this b dot t, bt dot c dot ct, this is a scalar dot product. So, this is a scalar function. So, real valued function of t. So, when you take the derivative, there should be another real valued function of t. So, we dot product dot itself has to be used here. Now is the important rule, it is the cross product rule. So, if there is a dot product, there is a cross product, then how do we handle the cross product? Because we have to now understand the cross product is a vector, it is a vector valued map. So, the derivative has to also be a vector valued map, right. So, cross product rule. So, these rules become very helpful when you are studying many problems in natural sciences, especially physics and in mechanics. Mechanics is the key to many developments in the sciences, especially for the physical sciences, and if one has to understand physics very well, understanding classical mechanics is of fundamental importance. So, when you do this, Again you have to keep in mind that we are now talking about cross products. Plus Bt into the cross product of C dash t. So these are the two rules, important rules, dot product rule and cross product rule, and this is something that you have to really keep in mind. So for the dot product rule, derivative of Bt dot product with Ct plus Bt dot product with the derivative of Ct. The same kind of thing with the dot product changed by cross product. So this, here it is a scalar, here it is a vector. And the last rule is of course the chain rule. This is an important rule. In the chain rule, what do we do? In the chain rule, what we do is the following. So you take a scalar function qt, so it is a number t, say it lies between a and b, then qt is a scalar function. Then you consider the function vector function c of qt. So it is a kind of composition. Basically it is c, this is it, is a composition of two functions. Now you are asking what is, not sorry, I think c should be given a blue color, that is what we are trying to maintain. So vector functions are blue colors. As I am just deciding my own this sort of colors as I am going on, just trying to make it look little fancy. And I could just written everything with black. You can write down what you prefer, whether you prefer this coloring game or you can, I should write just black. You can put in your opinions. Now the question is, what is ddt of qt? What is this? The answer is, here is the vector function, so answer has to be vector function again, answer has to be vector. Q dash t into c dash of qt. That is the chain rule. That is the chain rule. Okay. First you take a derivative of c with respect to qt and then take a derivative of q with respect to t. So it is a scalar multiplication of a vector. That is essentially the chain rule. If you write down this in the form of the first principle notion of a derivative in one variable, the variable t, you will get this. You can try this. Can you prove this? Okay, let that be a kind of homework for you. When I give the homework, it's slightly serious if you want to learn the subject. Is that not that I am just blindly giving you homework. I have thought about which thing to give as a homework. Why didn't I give you the dot product rule and cross product rule as homework? Because it doesn't let you think a bit, it's just a kind of mechanical thing that you will do. But here you will just think a bit, derive it from the first principle, prove the chain rule from the first principles. Okay. Because you have to understand, please understand, when I write this, what does this mean? It simply means x1 qt function of one real variable to one real variable, this is one real variable, x2 qt to xn qt. So, when you take the derivative, you have basically apply chain rule on all these n different real valued functions. So, once you apply chain rule there, you will immediately understand what the answer would be. So, I leave this to you as an homework. Okay. So, let me just give a small example of how this rule can be applied. So, consider a particle. So, consider a particle moving in a circular path whose center is the origin. And at any point t, this is the vector rt. What you know that the length of rt is constant. So, this is called circular path, circular motion. And at every point the velocity is tangential, velocity vector which is r dash t is tangential to the curve. And how do you know that it is tangential to the curve? Because rt is essentially anything that is perpendicular to the radius is the tangent. The tangent must be perpendicular to the radius. So, how do we know that r dash t, the velocity vector, is perpendicular to the radius? So, if you have a circular motion, so what do you know about a circular motion? That the radius, the length of rt, that is norm of rt, is constant, it does not change, which of course implies norm of rt square, which is rt dot product, which we already know, does not change, is constant. Okay. Now we take the derivative. I know that if this is constant as a scalar quantity, this derivative must vanish. So, ddt of rt dot rt is equal to 0. Now I apply the dot product rule, and I am sure you remembered now what is the dot product rule. The dot product rule says, here I will put r dot t because I have spoken of a particle moving along a curve. So, it will be r dot t dot rt plus rt dot r dot t, which is 0. So, twice of r dot t dot rt is 0, and that implies, and the whole thing implies that r dot t so the velocity vector which is always tangential to the curve is actually perpendicular to the radius. The radius actually acts as the normal vector. So, the velocity vector, which is r dot t, sorry, I should write it here as r dot t also, which is r dot t, has to be perpendicular to the radius vector, which is an application of the rule that we have just learnt. We have learnt earlier how to talk about acceleration. We have learned earlier how to talk about, for example, force and Newton's law and write it in a vectorial form. For example, if I take RT and describe it through this set of coordinate functions x t, y t, z t, then the velocity vector, velocity vector v t is equal to r dot t is equal to x dot t, y dot t and z dot t, and the acceleration at is given as v dot t is r double dot t and is given as x double dot t, y double dot t and z double dot t. So, if m is the mass of a particle, how do I express Newton's second law of motion? Newton's second law of motion. I recently visited a restaurant which is called ISACT Newton. ISACT, S-A-C-K-E-D Newton. I said, oh my goodness, who has this capability to sack Newton? Later on I realized, as one of my friends pointed out, that it is not Isaac Newton, that is called Isaac Newton, which they have just played with the words and written Isaac Newton. So, Newton remains to me, and I am sure to many others, as the greatest scientific mind ever. And even Albert Einstein had once spoken about Newton in the following words, that nature to him was an open book whose letters he could read without effort. I think everybody, I do not know whether I have mentioned in this course, but I think everybody, even if I have mentioned, I mention it again. Every viewer, I would request you to, from the net, wherever, you should read not the Principia itself, but the preface what Newton wrote in the Principia, and you will learn the essence of doing science from that very preface. You will see the clarity of thought that is embedded there. So that once you read that preface, you would come out as somebody who would start enjoying science. That's what my guarantee is. Now, how do I write Newton's law? Let us make it more colorful. Force should be red. So, the force vector, which depends on the position r, of course, or t I should write, if that's what it should be, is mass times acceleration vector, which is everything is in terms of the RT. So, this is the Newton's second law of force. One of the most important laws which Newton has enunciated is the universal law of gravity. And how do we express it in the vector form? That is very important to note. So, let us talk about the universal law of gravitation. What Newton proposed, and this comes from experimentation, these laws were not written down in the air, that one day morning after taking English breakfast Newton decided this would be the law of the world. No, Newton was interested in understanding tides, why tides occur. He could figure out, or he could imagine, that's called a leap in imagination, that the moon must be attracting the water on the surface of the earth, while earth also is attracting the moon and keeping it in the orbit. But that idea that bodies attract each other, and what should be the quantity of the force by which they attract, magnitude of the force by which they attract, that was laid down through what is called the universal law of gravitation. So the magnitude of the force, if there are two masses, one is m1 and one other is m2, there is a kind of invisible force by which these two are attracting each other. Of course, the forces are equal and opposite in direction. M1 is pulling on M2 and M2 is pulling on M1. But you know very well that the force is given, force is proportional to the product of their masses. The bigger the masses are, the forces is more. While as you take them away from each other, the forces become less. An apple, which is, if I hold an apple here, because everybody talks about apple when they talk about Newton, so I didn't wanted to make a difference. So you drop it, it will immediately fall on the ground. But while the moon is not falling towards you, it's because as the distance increases from, say, the earth, the pull of the gravitational field, the pull of that force becomes weak. This was a very great understanding. So it is inversely proportional to the square of the distance. And this F is written as G. I will not write down what is G's numerical value that you can get from any physics book. This is the magnitude of the force. It is the magnitude of the force. It is not the vectorial representation of the force. So what is the vectorial representation of the force? So suppose the distance between the two forces is given by this r vector. Suppose one particle is at the origin. So m1 is at the origin, and m2 is somewhere, and this distance between m1 and m2 is given by the r vector. Okay. So suppose this distance is r. How do I vectorically represent this force? So this force itself has to depend on the r. As the r changes, that the distance between the two mass change, the force, suppose one mass is moving away from the other, that is how heavenly bodies move away. The galaxies are moving away from the earth, from the point of vantage point. If I take the earth as a vantage point, then the galaxies are all moving away from us. We are living in an expanding universe, and that's what our evidence at this moment that we have, that is all the evidences point towards that. So hence here, if I look at this, so this is the magnitude of the force, but what is the vectorial representation of that force? The vectorial representation is that F vector is equal to G into m1 m2 by r cube into r vector. That is the vectorial representation of the force, because if I now take a magnitude of this force, which is norm of F, then I will have G times m1 m2, these are all non-negative numbers, by norm of r. Norm of r vector is this nothing but r itself, so it will become G of m1 m2 r cube into r. So this is nothing but G m1 m2 by r square. So that is what the Newton's universal law of gravitation is, and that is how it is represented vectorically. So this is very important to keep this vectorical representation in mind. Vector representation. Vectorial representation. Now let us see, if I want to write down, suppose here is a massive object, suppose there is an object like M is the earth, whose center of mass, if the earth sometimes, even they are massive objects, for the purpose of understanding can be viewed as a particle whose all mass is centered at a point inside the body, and that is called the center of mass. If I put the center of mass of the earth, this is the earth, at the center, that is the equator that I just drew. So this is the earth. And the mass is m, and let this be the moon, black moon, don't worry, I am not right, moon is white, but I am just writing it. So there is a force of gravitation acting on it here right away, moon with mass m. So what is the force? So suppose the distance from the origin, the moon, is at a distance r, rt basically. So m of r dot dot t, that is the force acting on the moon, mass into acceleration, must be equal, because the force is towards the earth. So anything that is towards the earth will take negative, because essentially if I write down, if I decompose the force into three components, x, y and z components, the y component will always be downward. So we will give a negative sign, right? So we are not moving from, what is the positive direction of r? The positive direction of r is from the origin here, O, the center of mass of the earth, towards the moon. That is the positive direction. But here the force is acting along the radius r, but acting towards O, so it is in the negative direction of r. So as per the law of gravitation, I can write this as minus g m r cube into r vector, where r is actually rt I should write, but okay, I am not writing rt there. So this is my r vector, this is the r vector, and the force is actually acting along the r vector but in the opposite direction, and that is why you take this force in this format. So this is the way you write it. Okay. Now can this be used to understand, can I use this idea to understand a very simple situation? Now consider a mass, I don't have space here, I would have done it here, but okay, let me just do it. Here I will just keep on writing in black, it is as if I am doing a mechanics class. So you take a circular path, good circle, so this is the center, let me take the coordinates going through the center. So for any particle, what happened? Okay, well done. I don't need to clap myself, pat my back. So this is the position at any time t for a particle moving. So assume they move with a fixed velocity s, the velocity vector is constant, right? Now how do I express? Suppose norm of RT is R. See here the direction of the vector RT is changing, but the value is fixed. So now here is a particle moving with a speed that is norm of R dash t, which is fixed. So how do I represent RT? Can there be any simple way I represent it in terms of S? S norm of R dash t, which is a speed, is constant. Now this angle theta t, so I can write everything xt as r cos t in a polar coordinates and r sin t. So r sin theta t. So what is this theta t? Now this theta t is actually nothing but if theta t into r is the distance travelled in time t with velocity s, that is s into t. So theta t is equal to st by r. So RT can be represented in the following way. It's r into cosine of st by r and r into sine of st by r. Okay, up to this okay. Now I take its acceleration. Now I compute r dot dot t, and I want you to check it for yourself that this will be nothing but minus s square r square into r vector t. So you see the sign automatically comes to be negative. So the force that is acting on the particle, this is the particle, the force that is acting on the particle will have a direction in this. This is called the centripetal force. So will be towards the origin along the radius vector, so that the sign is negative. This is called the centripetal force. Now of course the body also tries to, so there is on the body there is a centripetal force. So body puts a, so there is a force on the body, the centripetal force, and there is a centrifugal force, which is actually a force which is acting towards the body but away from the, acting on the center but towards the body. That is called the centrifugal force, which seems to throw you out of the trajectory as you move. So this is a centripetal force, and now suppose I have a body, suppose I have a circular body instead, suppose I have a heavenly body, suppose the moon is now moving in a circular orbit instead of whatever elliptical orbit that we think. If the moon is moving in a circular orbit, okay, then I can now use what I have learnt here and what I learned from here, that okay, now I can say that I know m r dot dot is the force, and what I have learned is what we have used for that mass of the moon and the earth system. We can now use it very carefully and write this is equal to minus g m m r cube by r t. Now you take the norm of both sides, minus will cancel, and if you take the norm of both sides, taking the norm, what would you get? You will get ms square r square is equal to gmm r cube, or you would get s square is equal to g m by r here. That is what you will get. That is what you can conclude. So, you have some idea of the velocity s. Now, in physics we say that the time, suppose a particle starts from the x axis at a point x0 and moves along the circular orbit and comes back to x0, the time taken to complete one revolution, one complete revolution. So, the moon starts here and you will observe the moon. So, the moon goes like this around the earth and comes back here. This time that is taken is called one period. That is the time that it takes to go around the whole circumference. So, let t be the period of the moon, period of the moon. So, if the moving at the velocity s, fixed velocity, let us assume, then what is t? This is nothing but 2 pi r, circular radius, by s, the velocity. Okay. So, I have s is equal to 2 pi r by t. So again putting it back into the force equation from what we have obtained about s square, I will have 4 pi r square t square is equal to g m by r. So, g m by r. Now, so this means t square is equal to 4 pi r square into r by g m, which means 4 pi by g m r cube. So, t square is a constant 4 pi by g m into r cube. So, what does that tell you? It tells you a very simple fact. It tells you that t square is proportional to r cube, and if you have learned some physics, does this ring something in your mind, ring a bell? I am sure those who have learned some physics, this will ring a bell. This is called the Kepler's third law, by which he says that a body, a smaller body orbiting around a bigger body, like a planet orbiting around a star or sun, the square of the period is proportional to the cube of the radius. The radius keeps on changing RT, but the period, the r cube t, because it is a circular orbit, the radius is fixed. So, this is proportional to the radius. This is called the Kepler's third law. So, there of course, if the radius is changing, like the one in the case of earth, you can represent it, it will still be that the square of the radius, a square of the time period is proportional to the radius. So, but here because we have taken a circular orbit, this r is fixed. So, t square, the time. So, whatever we, for any, if you increase the orbit, if you increase the radius, if it is much farther, then the time taken to rotate is much more, because it is proportional to r cube. So, what we get back after all these discussions is we end our discussions with Kepler's third law. So, of course, the first law are that okay, they go in elliptical orbit. Here we have made it more simpler, taken only circular orbit. Kepler actually studied huge data which was accumulated by his teacher Tycho Brahe to actually come to that conclusion, not by mathematical means but by empirical guess and testing and observation. So it's hard science and lot of calculations. So with this I end this talk here, and we will be talking about how to compute arc lengths. So how velocity, the idea of velocity can tell you how to compute an arc. Suppose there is an arc, I give you a curve like this from point A to point B in space. What is the length of this? This can be obtained by a very simple formula. The distance is velocity into time, and you will see how this very complex looking thing, this curve, and you want to find a length, can be found based on this very simple idea. Thank you.